we get on the output is then going to be the product of the two, and you're correct. But we're going to make that just slightly more formal here as we proceed. We form for the channel, just like we did for the signal itself, a sum of the in-phase and quadrature part. Now this may not be easy to see for the channel. It is easy to see for the signal itself because you just look at your modulated signal and you see the sine part. Something's multiplying sine, you pull that out, that goes here. Something's multiplying cosine, you pull that out, okay, and that goes in the real part. That's not at all clear for the passband channel. However, we also saw another way of getting that passband channel would be just kind of, suppose this is no longer an X, we just go in here and we write an H. I mean, the mathematics will work for that just as well. So we could get a baseband equivalent if we want it, and we'd take the real and imaginary part of that. So we'd slide the thing down to the origin, multiply by 2, and then inverse transform to the time domain if we wanted. We would get the real part h of I of t, and the imaginary part we get h cubed of t. Similarly, HA of t is also defined as the sum of h of t plus j times the Hilbert transform of h of t, and again we would get that by doubling the positive frequency content of the original Fourier transform. We could inverse transform to the time domain and we would get h of t for the real part and the Hilbert transform for the imaginary part. Okay, next step. Suppose I have the relationship which I already know is true for the original channel. I have x into a linear channel convolved with h of t, have an output y of t. If we take the Fourier transform, we know that's the same as multiplication of the transfer function of the channel times the Fourier transform of the input. Let me take that entire equation and multiply by 2. And then look at omega greater than 0. Since we know these are all real signals to begin with, then what's going on at negative frequency is simply a mirror image of what's going on at positive frequency. I really don't need to look at the negative frequencies. And if I do that, then I could simply write, because I have 2 over here, at least for positive frequencies, is that ya of omega is equal to h of omega times x a of omega, right? Because I've just recognized that for positive frequencies that 2 times the Fourier transform is the analytic equivalent. And then if I slide that down to baseband, then what I could do is let omega go to omega plus some carrier frequency, omega sub c. And if I do that, what I'll get is y of omega plus omega c, but that's y baseband of omega. And the same thing happens on xa when I put in omega plus omega c. But what happens in the middle is I get h of omega minus omega c for that transfer function, because I've just translated the frequency axis. And this here is 1/2 of HBB of omega. So we could actually write, or we could draw a little diagram again. We had it earlier. XBB of t basically goes through a channel that's 1/2 HBB of t, and I produce YBB of t. So outside of that factor of 2, which is just basically representing, I've kind of doubled everything because I got the signal and then I got its Hilbert transform too, or I have the and so what's happening is essentially I've doubled the energy in this description artificially of baseband signals, and so I got double the energy here, double the energy there. I better not use double the transfer energy, or I'm going to basically kick up the gain in the system artificially when I do that. Yes, sir.
Is the h of omega have a minus, should that be a plus mechanism?
No, I think not, because, let me see here. Yes, should be, sorry. Move that down to, that's moving to the left, your guys' direction that way in frequency, thank you. So, this is our complex baseband system. And the advantage of doing this is the carrier frequency is now basically removed. Everything's been centered around the carrier frequency. We don't have to worry about an analysis that would have to actually consider each and every carrier frequency. How do we get the channel? Well, we just look what's going on around the carrier frequency and take the Fourier transform and just slide it down to 0. And that's what goes inside this box, which is, in fact, 1/2 the baseband equivalent of the channel transfer functions itself. Okay, so let's, yes, sir?
Why did you use an analog equivalent for the H of omega t?
Sorry, I couldn't quite hear. Yeah, could you use the microphone too for the students in TV? Sorry.
Why don't you use an analog equivalent for the H of omega
Why didn't I use the in the upper one? Well, because I only had one factor 2 on each side of the equation. So I used it over here for YA, but I used it here for XA. So I didn't, if I would need another factor 2. I could write, if you like here, I could write 1/2 HA of them, and that would work. Okay. Any other questions? All right, let's look at an example. And this is the same example from the notes. We have a H of t that happens to be 2 times 10 to the minus 6th times sinc of 10 to the 6th t times cosine of 2 pi 10 to the 7th t. All right, we look at that and we say, okay, here's my carrier. That's F sub c there. And clearly, I've got a symbol right here. 1 over t is 10 to the 6th. Okay, so it's a megahertz. In describing this, this is a channel. Okay, that looks like it has. You see the 2 out in front here. Okay, for the system. What would happen? Okay, is if I found the complex equivalent of this, it'd be pretty easy. This part here is HI of t, because I happen to have it in a form where I can recognize the cosine. HQ of t would be equal to 0. Okay, when you see in a channel that the quadrature part is 0, basically what that means is there isn't going to be any phase distortion in the channel. Usually the imaginary part of the channel conveys, okay, essentially the amplitude characteristic. If I were to draw what this looks like in terms of frequency, then up at 10 to the 7th, okay, basically I have a flat transfer. Its amplitude is actually 1, and it goes from 10 to the 7th minus, it's actually 10 to the 6th over 2, 500 kilohertz if you will, and 10 to the 7th plus 10 to the 6th over 2, which is 500 kilohertz, and then of course I'd have the image at negative frequency. So we can see this clearly an ideal bandpass filter by looking at it that way. We could also, all right, form the baseband equivalent, in which case we no longer have to worry about the carrier frequency. We're going to double the amplitude, and what I'm going to have here is 0, and then 500 kilohertz here, and minus 500 kilohertz there, and an amplitude of 2. So this would be HBB of F. So that looks like an ideal low-pass filter. Just slid it down to 0. Now note this one is symmetric, both sides of the origin. Doesn't have to be. We could have, this actually has a real, okay, inverse transform because it's symmetric in amplitude. It's got zero phase in this particular case, so it satisfies the conditions. When it is symmetric around the origin, okay, then what that's telling us is essentially the same thing is happening to any signal that passes through this channel. Same thing happens to the real part, the in-phase dimension that multiplies cosine, as happens to the quadrature part, which is the sine dimension. So there's no phase distortion. There's no moving of something from the in-phase dimension into the quadrature dimension, or vice versa. Well, that's a channel that doesn't have phase distortion. Not all channels are free of phase distortion. In fact, most of them do have phase distortion. They're not exactly symmetric around a carrier frequency. And what will happen is the two basis functions are going to basically creep into each other's domain. They won't be orthogonal anymore at the output of the channel. They were at the input, but they ran through a filter, and there's no guarantee as they come out of the channel that they're still orthogonal. So we're getting some interference between the basis functions. We may also get interference, which we're going to talk about on Thursday, between successive transmissions. When we have an impulse response that's not a delta function. Even if we design the basis functions so they don't overlap in time, or they go to zero at just the right places in time, that's not necessarily true anymore at the channel output. So if I got something that wasn't symmetric here, if I had some other function, let's suppose, was maybe almost symmetric, but kind of looked a little bit, like that, then what would happen is I'd get that same kind of behavior over here, wouldn't be symmetric, and that would key me that I've got the in-phase dimension creeping into the quadrature dimension for QAM. So the constellation on the output of the channel is not going to look real nice anymore. Even if I started with my 16 QAM, the points are going to get distorted. They're going to be moved as that happens. Okay, so that's the channel. So you kind of get the idea. It's not a real hard concept. You just slide it down to zero and you take the inverse transform. Now you got a complex channel, complex impulse response that you can work with. So we can take a QAM signal, pass it through this complex channel, and get the output. Now if we happen to have real signals like PAM, we have the same diagram naturally. We have an input that's only real, and a channel that's only real, would be an H of T, and an output that's only real for PAM. So by introducing this complex analysis for QAM, what happens is now I just change the input to be complex. I got to know how to get the channel, but that's pretty easy. I have a complex channel, and I have a complex output. If I use complex functions with real and imaginary parts, I'm going to be able to analyze intersymbol interference or channels with H of T that are not delta function for both PAM and QAM with exactly the same analysis. And for PAM, I just throw away the imaginary part. And for QAM, I don't have a zero imaginary part. So we're going to be able to get both analyzed in terms of so-called intersymbol interference and equalization theory, which is a big part of the course that's coming in Chapter 3. So that's the reason for these baseband equivalents. Now we've covered the signal, we covered the channel, we got one more signal that we need to consider, and it is the noise itself. And normally we think of the transmitted signal. It is true it's somewhat random in that I have a few messages that can be sent, and so if I say they're all equally likely, then of course that we think of the input as random in that sense. But after I've already established which message is going to be transmitted, we think of it as a deterministic signal, X of T passing through the deterministic channel, H of T. The noise I have no control over as a designer. That just basically gets added. Okay, it's random. So it's a random process, and so we have to exercise a little bit of caution with baseband analysis when we deal with random processes. In particular, the noise we've been dealing with is white. It's also Gaussian. But what's important here is that there's white. And so we could try to take a Fourier transform of noise, but if you remember back to your probability classes, especially if you had a rigorous instructor for this, say you cannot take the Fourier transform of a random process. Okay, you can only find its power spectral density, or you can only find its autocorrelation function. It has no Fourier transform, strictly speaking. But let me just have an abusive notation. Let's say I have some additive noise, and in effect I'm kind of drawing the power spectral density. But I'm saying, well, I happen to get lucky with one of the sample waveforms from the noise, and it is actually white itself. What's really true is the average over all of the input Fourier transforms, which is the power spectral density, when you square it, would be flat. Well, let's think of it that way. If for each and every sample waveform I were to form an analytic equivalent, well, we know how to do that. That's n of t plus j times n check of t. And that would look like this. 2. So NA of f is going to go out to all frequencies with amplitude 2, and it's going to be 0 for negative frequencies, because analytic signals never have any negative frequencies, and that would be true for each and every one of the sample functions that we look at. Okay, so that is true for all the sample functions. Let's look at the power spectral densities, PSDs, abbreviated here. Now I call the power spectral density Sn of S, or spectrum, basically S. N is the random process, and F, of course, is the frequency variable. So I have an N of T, and I can correctly write that its PSD is some level N naught over 2 for all frequencies. Now, if I were to form an A of T and look at its power spectral density, well, on average here it's kind of 2, but this is for the waveform. The power spectral density squares the noise. We're looking at the average squared magnitude. So if I have a 2 here, I'm going to have a 4 when I do this. So now I have not N naught, but actually N naught times 2. So this is SA of F, the power spectral density of the analytic equivalent. That extra factor of 2, factor 4, it has to do with the fact that I'm squaring amplitude. So instead of going up by a factor of 2, I go up by a factor of 4. And then, so I could actually write that this is 4 times Sn of F for F greater than 0. Now I'd like to go to the baseband equivalent, and we know what to do for that. If we have some carrier frequency in which we are interested, then we slide everything to the left by that carrier frequency. So what will happen is now this, I'm going to drop a dotted line here. This would be minus F sub c. This would be 0. And this would still continue out to infinity. And if I only care about signals that are somehow around 0 there, my carrier frequency is selected large enough, then there's no harm in just extending that back out to minus infinity. I've got extra irrelevant noise. In that case, it's at frequencies I don't care about, just like I could throw away frequencies I didn't care about when we talked about irrelevance, white noise, earlier. And so what I have is SBB of F being 2 N naught for all frequencies. And so with white noise, essentially the baseband equivalent is still white noise, but it happens to have 4 times the power spectral density, or equivalently, if I were to inverse transform this to the time domain, it'd be a delta function, and it would be 2 N naught times delta of t, and that would be the autocorrelation function, a spike at the origin. So this is how we handle white noise. Now, if I actually had correlated noise of some type that didn't have a white spectrum, well, that's fine too. I simply slide to the left and multiply by 4 the power spectral density of that noise. So for any stationary noise, and it has to be stationary to have a power spectral density, then SBB of F is 4 times the power spectral density of the noise slid down to 0. All right, so that's the noise, perhaps not too surprising at this point. That result, the only thing new with respect to the signals was, since we were dealing with power spectral densities now, the multiplying factor is 4 instead of 2. All right, so now I'm prepared to go after my third topic, which is basically the channel and its output. What do we do? What does a demodulator look like? So I wrote demodulator earlier for this consistency and scaling, which is really, what does a demodulator look like for such a system? We're going to have